Hello everyone, my name is Tyler, and today I'm going to be going over how to implement tile cost into a tactical RPG game. This video is based off of Radical Oyster's video, where he goes over how to do this in Godot 3. Because of some slight changes between the engine versions, I felt that this video was necessary to create, and because I plan to make more videos explaining on how to implement various other features of a tactical RPG, such as attack ranges and unit collision based on team. Those features all require the movement system to be functional, so think of this as video 1 of a series. Now this is being built off of GD Quest's tactical RPG movement series, so I highly recommend that you give that a look before watching this video. You will need to download their Godot 4 version of the project from GitHub, which I have linked down below with other useful links as well as the link to the GitHub repository where I have completed the code from this video. And with that out of the way, I'll be going through the necessary steps very quickly on how to implement tile cost to cells with the use of Dijkstra's algorithm. This is all assuming you have some familiarity with Godot and data structures and algorithms, as well as other various basic coding principles. Okay, so the first thing that we're going to want to do is we're going to want to move the map under game board. We're going to want to open map in the editor. Select map if it's already not selected, and then we're going to move down here and click Tileset. From clicking Tileset, we want to pay attention to the Atlas IDs that we have here. Now, we're going to delete these two tiles for the purposes of this video. We're going to drag in another Grasslands PNG. We're going to click No. Now in this recording, my Atlas ID is 5. That's because I've done previous takes. But if it's 2, you don't need to edit it. But if it is something other than 2, we're going to click Edit. We're going to change this to 2, and then we're going to click OK. We're going to go back to this tile set right here. We are going to want to look at the, let's see here, texture resolution. We want this to be the same. So we're going to need to make sure that these are 80 between all of them. We will change that. There. And then we're going to want to select this one, enable this for Atlas ID 1. And then for Atlas ID 2, we're going to click this one. Okay. So the purpose of doing this is to designate certain tiles that are enabled in specific tile sets to have the Atlas IDs that we want them to have. The reason for this is because later we will create a dictionary and code that will call these IDs to determine the cost of a tile. Alright, so now we're going to right click tile set under tile map in the editor. We're going to click edit, and then we're going to go down here and we're going to click new GD script. We're going to then click edit. And then we're going to want to do Control S. And we have saved it now. And with this, we're going to do @export var movement underscore data. And we're going to make it of type dictionary. Save that. Okay, now if we go back to the 2D scene, we click on map, and then we go and edit tile set again, we'll see that we have created a dictionary. And with this dictionary, we can now call and define the cost of moving on a tile based on the Atlas ID of the tile sets that we have here. To add entries, all we do is we click on the dictionary, and then we're going to set both of these to type int. Now the key will be the Atlas ID, and the value will be the cost of moving onto the tile, so the movement cost of the tile. Now these Atlas IDs are what I defined earlier, which is 0, 1, and 2. For key 0, we're going to set the value to 1 because this will be a regular tile that we move on. Do int again. For Atlas ID 1, we're going to set the value to 2. This will be a tile that costs a little more to walk on. And then for Atlas ID 2, we're just going to set the value to an absurdly high number, like 5 nines. And the reason for this is because we're trying to make a tile that's pretty much just impassable by our units and acts as a wall of sorts. Okay, so from this point onwards, this video will be pretty much the same as Radical Oysters video, since we'll primarily just be doing some coding now. He does a much better explanation than me for how all this works, so I definitely recommend you go watch his video at timestamp 7 minutes 11 seconds. However, I will still go over everything that he does and try to explain it to the best of my ability. Okay, so next we're going to attach a script to the map node. Mapgd is a fine name. We're going to delete everything except the ready function and the extents element. We're going to create a variable called movement_data. And then we're going to assign movement data the dictionary that we created earlier from the tile set of the same name. From here, we're going to create a function called get_movement_cost. And we're going to pass it the grid that is attached to game board. And essentially, this is why at the very beginning we moved map under the game board so that we can access this grid. Now, looking back at our code, we're going to create an empty array called movement cost. And now we're going to traverse through the grid in its entirety and acquire the movement cost of every single tile that is placed. So to do this, we're going to do for y and range of grid.size.y. And then there, we're going to do movement_cost append. We're just going to append an empty array here because we're going to insert data into that array. Then we're going to do for x and range grid.size.x. Then we're going to do var tile equal to get_cell source ID. Oop. Wrong one. Source ID. And then we're going to do 0 vector 2i, and then we're just going to do x, y. This is us grabbing pretty much the vector coordinates of the current cell that we're on. And what's really important is this 0, because what this 0 signifies is that this requires that all tiles with a movement cost must be on layer 0 of the tile map. So every tile that you place must be on layer 0. It must be on layer 0, because if it's not on layer 0, this won't work. Okay? And then from here, we do var movement_cost equal to movement_data.get tile. And this is us grabbing the data based on the vector coordinates of the current cell that we're on. And then we are going to append that data to the arrays that we have, or the empty arrays that we have. when all is said and done, we are going to return our movement underscore cost. But yeah, to go over once again, essentially what this function does, this function gets the movement cost of any single cell on the map. And we pass in the grid so that we don't take in the data from tiles that have been placed outside the play area. Quick correction. I said this finds it, takes in the vector coordinates. Well, that was actually wrong. Essentially, we're getting the Alice ID from coordinates of the cell, and then we're taking that Alice ID and putting it into the dictionary and finding out what the correct cost is. Besides that, we can finally go on to our main scene right here. What we're going to do is we're going to go down to our file system. You're going to create a new folder. We're going to call this data structures. See here, and then within data structures, we're going to create a new script. We're going to call this script LinkedNode. Going to open up LinkedNode, and we're just going to delete all of this. We're going to do class name is LinkedNode. We're going to do var, which is the value. I believe these are the coordinates. I think you'll have to do your own research on Dijkstra's algorithm, LinkedNode, in the priority queues or whatever it is, because while I might have used them before, the in-depth explanation isn't my best ability, which is why I highly recommend you do go watch Radical Oyster's video if you have any questions as to how things work, so that you might have greater control and greater variability in what you're dealing with if you come into any problems. And with this one, we're going to do var next, and we're going to make this of linked node. And essentially, this is just like the next node that is on the linked list, so that we can keep traversing through the list after the current one that we're on. And now we're going to do function initialize, and it's going to take in 3 parameters. It's going to take in node value, which is a vector2. It's going to take node priority, which is of int, and then it's going to take next node, which is of linked node. And we're going to set this equal to null. And I'll just do pass real quick so I can write out what's going to be happening in this function. So essentially, when we create a new linked node, we will define the properties of the node. So this is our constructor function. The equals null on next node essentially just means that when we create a new node, and we only pass 2 parameters, there's like with no third value. Then the next node will default to null. Okay, so for the initialization function, we're going to do value is equal to node underscore value. We're going to do priority is equal to node underscore priority. And then we're going to do next is equal to next underscore node. We're going to have to create 2 more functions. Those functions, or 3 more. These are going to be our setter functions. And the first one is going to be function set underscore value. The third one is going to be, or I should do it one at a time. New underscore value vector 2. And this is value equal to new underscore value. Second one will be set priority. Let's see here. Priority equal to new priority. And then the final one will be set next. New node, next equal to underscore node. See here. All right. And that is us creating the linked node script. All right. So the next data structure or script that we're going to make is going to be the priority queue. Create that, open priority queue, and we're going to just delete all of this right here. Okay, so the way the priority queue works is that we only have access to the first element directly, but each element in that queue is linked to the element that follows it. So we could traverse through the queue one by one. Our implementation will have our nodes sorted by priority value, specifically from lowest priority to highest priority. This code is adapted from Geeks for Geeks explanation on priority queue using linked list. I will link that down in the description. But with that, let's move on to actually coding. So we're going to do class name priority queue. We're going to do var front. And essentially, this is the front node of our linked list. This is what we're going to retrieve to access the list to begin with. Then we're going to have new node. New node is just a helper variable, and then we're going to have temp, which is also just another helper variable. With that, we're going to go on to initializing. We're going to do front is equal to null. And then if our function is empty, we're just going to return that front being equal to null is true. Ooh, come on. Okay, so we're now going to do the push function. And essentially what the push function does is we're going to insert an element into our queue. We're going to take in two values, two variables. The first one is going to be value, which is a vector 2. And then the second variable is going to be priority, which is of type int. And this value is the cell we want to push into the queue, and then priority is the distance of the cell from our current position. And then the first thing we're going to do is we're going to want to check if our linked list is empty. Because if it is empty, then we need to put in something. So that's not empty. Yeah. Front equal to linked node dot new value priority else if it's not empty, we're going to do front dot priority is larger than priority. And what this does, this specific line, is we're using it since we want to find the shortest path from lowest to highest priority. So if you wanted to do the opposite, where you do highest to lowest priority, you would just flip this around to the other direction. So let's say you didn't want to say each tile cost 1 to move on. Instead, you wanted to make it to where it's like 5 is the shortest tile and then 4 is actually further away. That's kind of why you would want to do that. I don't see a reason as to why you would do that if you're trying to calculate shortest path based on the cost. This might be useful to change if you're dealing with AI, if you want to incentivize the AI to go to certain tiles that perhaps give them buffs, or to stray them away from ones that have debuffs. That is up to your own discretion, and I'm not sure how you would want to go through implementing that, but perhaps in the future I will make a video explaining. But for now, we're going to write down what we do in this section of the if. And this inserts our current node as the next node. And then we're going to have an else here, and it just is us setting it to a temp, the front node to temp, because our front priority is less than the current priority. Okay. And then within this, we will have a while loop. And this while loop is essentially us wanting to traverse through the queue until we find the right spot to put this node. Oops. And then at the end, we do new node equal to linked list of new temp dot next. Okay. I see temp dot next to new underscore node, and then this should be linked node. Okay, and with that, that is the push function, and now we're going to do the pop function. And this is just our way to get our node out of the queue once we're done with it. And with that, we have made our priority queue script. Okay, now that we have our priority queue done, we're going to go to game board. Here, you're going to make var underscore movement underscore cost. We are then going to do at on ready var underscore map equal to type tile map, then make it equal to capitalize that. This needs to be the exact same name as whatever you have it here. Same for these ones, right? Because it's calling it by the actual name of the node. And then on ready, we need to do underscore movement, underscore cost is equal to underscore map dot get underscore movement underscore cost grid. And now we're going to take a look at our flood flow algorithm, not because we're going to do any edits to it, but because this is what is determining the cost of our tiles right now. But we're going to use Dijkstra's algorithm instead of flood fill. Now, I will say you can delete this if you want to, if you do not plan to use flood fill. But in my later tutorials where I detect unit collision based on team and attack ranges, we do need flood fill still, so I recommend that you keep it there. And with that, we will move on to Dijkstra's algorithm. See here, let me pull up my code. Okay. And essentially, Dijkstra's algorithm will generate a list of walkable cells based on unit movement value and tile movement cost. That we will do function underscore Dijkstra cell vector 2 max underscore distance int attackable underscore check underscore bool. Do that, and then we will return an array. Do pass real quick. Let me check to make sure that I added something. Here we go. Up here at the very top, we need to make sure that we have a constant that is called max underscore value of type int. And we're just set this to an absurdly high number again. Going back down to Dijkstra's algorithm, we want to do var movable underscore cells is equal to cell var visited is equal to empty array var distances is equal to an empty array, and then var previous is equal to an empty array. And essentially movable cells, this appends our base cell to the array. The visited array will be a 2D array that keeps track of which cells we've already looked at while running the algorithm. Distances will show the distances to each cell. It might be useful. You can omit it if you want to. There's a variety of uses that you can have from keeping track of this, but I'm not going to go over that in this video. With the previous array, this is a 2D array that shows you which cell you have to take to get to the shortest path. And once again, you can omit this if you want to, but it could be useful in the future if you need to access this information. Now we're going to iterate over the width and height of the grid. I see what I did. I wrote the lines for the next ones, but I will quickly fix that after I do this next part. And we will just see here. Now make our new queue. We are going to add our starting cell. Essentially, we're going to make a while loop that, while there still is a node in the queue, will keep looping through and through and through until we reach the end. And we're going to do var cost, var distance to node, var occupied cells, for while not q.is score empty, do var current equals the q dot pop. This takes out the front part of the this takes out the front node, and then this will mark the front node as visited. For direction in directions, this is us traversing through, up, down, left, and right. So we're essentially just going to be going through all 4 neighbors of the current node. See your coordinates. If visited, coordinates dot y, and then coordinates dot x. Continue. Else tile cost is equal to square movement cost coordinates dot y dot x, and then distance node current.priority plus tile underscore cost. And this is us just calculating the tile cost normally. Then from here, we have visited coordinates.y, coordinates.x equal to true, distances, which is coordinates.y, distance to node. Then here we're going to check if the node is actually reachable by our unit. With this, we're going to mark the tile we used to get here. With this, we're going to attach a new node we are looking at as reachable. And then with this, we're going to use distance as priority. Oops. Then right at the very end, we will return movable cells. And with that, we have coded our Dijkstra's algorithm. All right, so now that we have Dijkstra's algorithm coded, we need to go up here and change underscore flood fill to underscore Dijkstra. And one thing that I did wrong, as you can see with this error, is that we have 3. Now, in a later tutorial, I'll be explaining how to draw attackable cells correctly, and that's why I have this check, but we're going to be deleting that because we don't need that right now. And then I made an error down here on line 128, var coordinates equal to current. We need this to just be of dot value. Let's save that, and now we can finally go to our 2D scene. Now, one thing with our 2D scene is that an error will occur if you set the size of the grid and you do not have every single tile filled in. So if I were to click on map real quick, we could see here that around 18, if you don't have a tile down that's in our grid. So this would give us an error that would break our code if we try running it. Now, obviously, you can just change the size of your cell so that it is within the proper bounds. If you don't want to program a camera and you want things to be just where they are with the camera not moving. But for the purpose of this tutorial, we're just going to do some painting real quick with our tiles. Make sure, by the way, to click the correct tile set. So we have 3 different tile sets, right? these are all our 1 cost tiles, these are all our 2 cost tiles, and then these are like our walls or impassable tiles. You want to make sure not to use tiles that are that look the same but are of a different Atlas ID, because then you would have multiple tiles that look the same but have different cost, which would be very confusing for the player. And while I'm not necessarily one to discourage against that, because you could do something very neat where you have, say for instance, like a hidden wall or something that the user could find while playing the game, which would be very fun to deal with. And could definitely be interesting, but I'm not going to be doing that here. So let me just quickly fill this in. I'm sure there's a much faster way with a hotkey from Godot, and I will link a video down below that explains tile maps, auto tiling, and such. But for now, we have our little area. We can put some flowers down. And now we have our 2 cost tiles. We're just going to be putting these down right here. And then we're going to have our walls. We're going to put like a line of walls all the way across the top here. Put some right here. Then let's make a little area where people can walk into so we can actually check correctly if they can walk in and out. Then we're going to save our scene. And let me click game board real quick. Click the bear. The bear has movement range of 3. Squirrel has movement range of 5. And then the cat has movement range of 8. Let's move this down to say 4 for now. Enter, save, play. Here you can see he goes 1, 2 because it costs up to 3. He can go up 1, 2, and then it goes 4. And as you can see, he can only move 2 down. And then if we see here who has 5, we can't walk past these walls that we actually have our pathing go around. So as you can see with that, we've implemented expanded movement in Godot 4 using Dijkstra's algorithm, a priority queue, linked list, and the like. If you like this video, you know, obviously the generic shill of like, comment, and subscribe. Definitely give Radical Oyster and GD Quest a look at the original works, because that's what this is based on. You know, show them support, because I obviously wouldn't be making this video and later ones without them taking that first step to really discover this kind of stuff. And with that, I hope you'll have a nice day. Goodbye.